Up next, Gernot is going to give us an update on R&D at Trustworthy Systems. Take it away.
Okay, thanks. It's a rare pleasure to follow one of my students in the next talk. So Lucy has talked about one of the things we're doing, which is the driver framework. And I want to provide a bit more general context of the various projects going on in Trustworthy Systems. And the main one is what we call, as of last week, the Lions OS. And as Lucy mentioned, push button verification. I'll talk about a bit what we do there. Pancake was already mentioned. I talked about that last year, and I'll give an update. And then I sort of have quick, brief snippets on other things that are on the burner. So first is the Lions operating system. Named after John Lyons, who was an academic at UNSW Sydney and known for writing what's called the Lyons book, which basically taught one or two generations of programmers about Unix in the 70s and 80s. And we are trying to build a system that's not for nothing called the Lions OS, because Lyons described Unix, which in those days was really a completely different approach to doing operating systems, based really on being simple and orthogonal. And by and large, the operating system community has completely gone off track and really forgot the lessons of Unix. And so we are trying to really go back to basics and do a principled operating system. So just to step back a bit, talking about SEL4, we had this great talk from Los Alamos Labs on how difficult it is to use SEL4, and there's good reasons for that, good or bad as you like. So SEL4 is really a very principled design. It's proper microkernel in the sense that it's minimal, policy-free, providing mechanisms only, policy built on top, and has a single access control mechanism. It's very security focused. It was designed from the beginning for verification. It was very performance focused. When we started it, I said we shall not lose more than 10% in IPC performance compared to previous kernels. We then got faster. And the idea of you don't pay for what you don't use. And in particular, we did not try to do what many other people do in operating systems, try to provide hardware abstraction, stop yourself from shooting yourself in the foot, and sort of aiming for usability, because that's all stuff you should do on top at user level. So you really need to think of the microkernel as the assembly language of operating systems. And too many people forget that. So the result of that is, if you look at SEL4 as your basis, then it's an extremely difficult thing to use. It's a really difficult beast. It requires a lot of expertise to design systems properly on SEL4. And that's, as we've seen, not really what you can expect from the normal users. So how do we get further? The first step in that direction was the microkit, which was mentioned already. Ivan will talk at length about it, where we did really two things. One, restrict the application domain to static architectures, but use that then to dramatically simplify the model to just a handful of abstractions, and I'm serious, it's a handful, countable on one hand in unary, not binary, and but in a way that's really very thin abstraction layers around the base SEL4 mechanisms, and sort of force you to produce good designs. There's still no guarantee that you will produce good designs on the microkit, but it's basically much more the default than the other way around. And as I said, Ivan will talk more about it. So the Lions OS is really the next step. Microkit as the basic framework, build a complete operating system on top. And the idea is to really do what you're supposed to be doing with microkernels, have a really modularized design. And this is not like what QNX, for example, thinks is modularized, where you have a process server and a file server and a network server. I'm talking really fine-grained modularity, basically what Lucy showed for the networking system, right, where you have separate modules for driver, multiplexer, copier, IP stack, etc. So we really want to apply this for the whole operating system, including file systems, what else you need. And then, of course, leverage the strong isolation guarantees you get from SEL4 to achieve all the good things like fault containments, etc. So this is sort of the basic idea. The specific aims we have is we want to build the best performing microkernel-based operating system ever. I don't think that's a huge challenge, but it's this is definitely our game. We also want to produce the most secure operating system, real-world capable operating system ever. And this means really comprehensive use of, or really extensive use of formal methods, formal verification. And we want to, at the same time, remain adaptable. And that's the challenge, getting all of these under one roof. And I believe we can do that by really going back to some basic principles. And the number one principle of the Lions OS is the KISS principle. Keep it simple, stupid. I just checked the other day where this comes from. Apparently it was created in the US Navy in the 50s or something. It's unfortunately the principle that's completely abandoned in all real-world operating systems. And going back to this, I think will give us a design that meets the three aims I said, put up on the previous slides. So that's the overarching principle. Let's distill that down to a bit more specific ones. Least privilege. I'll talk about them in more detail later. Strict separation of concerns. This is the sort of stuff we teach our first-year students and then forget. Radical simplicity. I'll explain what I mean with that. And use case specific policies. And among all that, design for verification, although that falls out, I believe, pretty much almost automatically from the others. So let's have a look at more detail. Least privilege. This is really a standard security principle, goes back to Salzer and Schroeder in 1975, so it's almost half a century old. It's as valid as ever. No component should have more rights than it absolutely needs to do its job. And the SDDF, as Lucy explained, is one example of that. It's highly componentized, and every component only has the privileges it needs. For example, as Lucy explained, the device driver does not have to have access to the data. All it has access to is pointers to data. It still can cause damage there, so that doesn't solve the problem, but it reduces it to something much more manageable. And in the SDDF, in the Lions OS, we want to take this further in really applying this to the whole system. And in particular, we will have two sets of policies. There is mandatory policy, and that is enforced by the static architecture. So in terms of what Ihor said earlier, this is a semi-static system. I call it a static architecture system. And the architecture prescribes if you like, an upper bound on the security policy on information flow. And on top of that, we'll provide discretionary policies that can further refine access to what's really needed. So the idea there is there will be executables that have a signed section of the actual rights given, and that will be enforced by the system when the executable is loaded. Okay, so that's least privilege. Separation of concerns. Again, Lucy demonstrated that on the device driver framework. The driver has one and only one concern, which is translating between a hardware-specific device interface and a hardware-independent device class interface, and nothing else. And everything else is taken in separate components, like the multiplexer, separated between transmit and receive, the copiers. I have a validator in there that can be replaced by a copier depending on the system you want to build. So really minimizing the concerns a component has to deal with, ideally just making it exactly one. And that obviously requires many modules, but as Lucy has shown with the driver framework, that doesn't have to impede performance. And one thing we learned there, as I said earlier, is an extra component, extra set of context switches on the path that the packet goes through costs almost nothing if you do it right. It's in the noise. And so when people complain about cost of context switches, performance, module crossings, etc., it's nonsense if you really build your system correctly. Next one, radical simplicity. And this is really sort of a refinement of the KISS principle, where we say, okay, every component should provide exactly the functionality needed and not a bit more. In other words, absolutely radically minimize the complexity of every of these components. And that's supported by a simple programming model, which we get from the microkit. So the microkit has strictly sequential code. Everything is simple event handlers. Things communicate via single producer, single consumer queues, which are really straightforward. And the static architecture, which obviously simplifies resource management, which is then mostly static. And if we apply the radical simplicity principle to policies, then we get a similar story. And this is really where operating systems have gone off the track. Traditional operating systems try to achieve really generic universal policies. And this is where a lot of the complexity in Linux comes from. It's obviously a huge source of complexity, and it really reflects a completely outdated model of computer use. It's the model of the departmental computer which we had in the 80s, which does file serving, web serving, well, not web in those days, FTP maybe, whatever, right? Interactive editing, all that stuff was done on one single box. We don't use computers like that anymore. Mobile phone is maybe the closest approximation to this these days, but even those are not so, don't really have this concurrent serving of really dissimilar use cases. In particular, in the embedded cyberphysical space, this model is completely misplaced. So we go back and go in completely the opposite direction of having extremely use case specific policies that are easy to replace. So for being adaptable, you don't need these universal policies. What you need is an ability to swap out one policy for the other. And Lucy has shown that with the multiplexer design. She implemented 3 or 4 different policies in the transmit multiplexer. It's just one policy each, and if you want a different one, you just swap in the other component. They're completely plug-in compatible. They have the same functionality, but they have different trade-offs implemented internally. And I believe that's the right model. And it's not even difficult to even swap those at runtime. We've done some initial experiment. We should be able to swap out one of these at runtime in a few microseconds, if you really need that, which is really doubtful for a cyber-physical system. And then design for verification, well, we have strict modularity, so we reduce every module to the absolute minimum. Radical simplicity, that itself should really aid verification, and I've got some evidence to actually back that up. Okay, so that's the design. We really just started on it, but we start looking for funding. We have partially the funding covered, not completely, so I'm still looking for more. Lucy's networking layer is a core part and really the template for building a lot of the other functionality, which is in the design by now quite mature, but fine-tuning implementation. We have prototypes for SD storage, NFS clients, touchscreen, etc. I wouldn't call the designs there final. This is sort of one of the things I need to focus on when I come back, and working on virtualized graphic. And this means sort of we're close to having an actual operating system there, and our aim is by December to release the first prototype. It will be fairly minimal in its services, and in some parts the design will still be preliminary, but it will be able to serve as an operating system for a real system. And Dale talked about a point of sale system, which just happens to be the demonstrator we will be doing. So first release in December, OS with an actual application on top. Will actually be in a box that functions, and we'll plan to use in the lab. And we'll have debugging or initial debugging profiling support as well. So this is really inherited from the microkit, and Ivan will talk about that. In first quarter next year, there should be a fairly mature release of the still restricted operating system, highly documented, and including some initial experience on verifying bits. And by the end of next year, and this is a careful, conservative estimate, we'll have a verification story of some key components. And the aim is, and this is very much subject to sufficient funding, is by the end of 25 to have the complete thing there. So this is the Lions OS. Next thing we're working on is, as Lucy mentioned, push button verification. So what is this? In SEL4, so far predominantly for verification, we used interactive theorem proving, and this is the bread and butter of our proof graph friends. They are the world experts in doing this. So interactive theorem proving means you do actually write proofs pretty much manually. The systems check them, so you can't do them wrong. It's very powerful in terms of the problems it can tackle, but it's also very labor intensive. So it's in a way an expensive but very powerful approach. So the SEL4 functional correctness proof and a lot of the other proofs are done in interactive theorem proving. The opposite of, or the alternative to this is push button techniques, particular SMT solvers, which also have been used in the SEL4 verification. So the binary verification, translation correctness proofs, they were all done in the end with SMT solvers. So these are things which use a smart state space exploration, which means that if things go well, it's fully automatic and relatively fast, but it's very limited in what it can prove. So this is why ITP is not going to go away. And they tend to be quite fiddly, etc. But the good thing is, once set up, it's all automatic. And the tricky bit is to set up the actual proof conditions correctly, so the proofer will be able to provide one of the answers. And the answers are, I have a proof, or it's correct, or I have a counterexample, or it times out, in which case you don't know anything and you go back to fiddle. And then the third relevant technique we're also employing is model checking, which is exhaustive state space exploration. And Lucy already said that we're using that for the intercomponent communication protocols. This is pretty much where model checkers are used. They're really good at verifying protocol properties. So this is not, we have some experience with this, and that's in particular with verifying the microkit. So in the microkit, we have C code, which gets imported into the theorem prover using the C parser that's been used for the SEL4 verification. That generates what's called the symbol language. And then there's a tool called symbol export, which exports that in the CTVGL. That's a graph language that describes control flow graphs. And that was also developed for the binary verification. So this is all reusing existing tools. And then you have to have a manual, or at the moment it's manually written specification of the properties you want to prove. And then we have a tool called Gordian, because it cuts through the knot, that produces the SMT problem. And then we can throw an SMT solver or throw it at an SMT solver, and it says yes or no or timeout. And this was used for verifying the functional correctness of the lib SEL4CP, as it was called then, now lib microkit. So that's the implementation of the microkit. So these things actually work for real code we use now daily. And that was a real eye-opener. Really, two results. I wouldn't give the same talk 9 months ago because I didn't know a lot of the things we learned in the meantime. To me, in the last 9 months, there were two major eye-openers. The one was the performance results Lucy got for the driver framework, the networking system, the drive framework, and the other was the results we got verifying the microkit with SMT solvers. And taken together, this makes me confident that we can do a real highly secure, high-performant lines operating system. With the microkit, there was also another verification story. So the microkit starts off with user-supplied SDF config, so that's the system specification, and then you write your protection domains and compile them into ELF files, and that gets supplied to the SDK, and the SDK tool munches that all up in an executable system. And what we also have now is an export of the system spec into CapDL, and the system spec gets also imported into Isabelle with a new tool, and the CapDL generated gets imported into Isabelle, and then there is a translation validation proof between those. So we have a verified translation of the SDK spec into CapDL, which of course means that, well, we can reuse existing things. So if in a microkit system, the system specification is specified in a similar abstraction level as the CamKit spec. And there's CapDL, which in a previous project, we have a generation of a verified initializer for this. Now, with this verified translation into CapDL, we have in principle, and I'll talk about the gaps there in a second, a way of generating a verified initializer for the microkit. And then, of course, that was the proof, the push button proofs I talked about. We have a proof of the implementation, functional correctness of the implementation of the microkit library. There's a few gaps here. The one is that the functional correctness proof has been done for the original version of the core platform, which is the fully static one. We have a much more extended functionality by that. We're redoing this, so that's in progress. The system initialization, there is a big hole there because there's a mismatch. The microkit uses 64-bit and MCS versus the original generator of the verified initializer was for 32-bit and MCS and non-MCS. And so this is not going to make progress until AH64 and MCS are verified. AH64 is around the corner, as Gavin said. MCS will be a bit longer. In principle, it's possible to downgrade the microkit to non-MCS. We've done that, but we don't want to maintain it. So if you want to do it, that's fine. It's not particularly difficult. And then there is the other spec gap between the SEL4 spec that's used for the SMT solver and the SEL4 abstract spec. So this is an unverified projection. And we don't yet know whether we can close that gap, but we're exploring that at the moment. I've got a good former methods person who knows the SEL4 proofs working on this one. I'm not promising anything. But the takeaway here is these push button techniques actually can do real stuff that's really enabling our work on the Lines OS. So I'm fairly confident that I'm not promising a fully verified OS, but I'm confident we will verify core components of it. And it's not going to take all that long. And the real enabler there is the simplicity of those components. Okay, very quickly update on other things. Pancake, I introduced last year. So this is our new language for verifying, for making it easier to verify systems code. And as Lucy said, this is work that's in progress. It's particularly aimed at easing the verification of device driver. So it's a systems language that's sort of C-like but safe. No fancy type systems. This is what we learned from the previous Cogent project. Fancy type systems are not good for verification. it does have a verified compiler and clean semantics, etc. And the idea is then, yeah, okay, it makes it easier to verify the logic of your component on top because it's a much better starting point. But we're also exploring using push-button techniques for that stage because Pancake can easily export the same format that was used for the other push-button verification, so this graph language. And that export is in progress, and the people said that shouldn't be a big deal. So we should actually be able to use SMT solvers here as well. Pancake has a verified compiler, thanks to tagging into the verified compilation toolchain or verified compiler of the CakeML language. It sort of tags into a lower level of a really deep stack of compiler passes. So that works. It's very much a rudimentary language at the moment, but it does have a verified compiler. So we know the code generated is correct. It's semantics preserving. At the moment, it's got a number of limitations. So we've implemented the multiplexers, both the transmit and receive multiplexers in Pancake. At the moment, it's not possible to do this purely in Pancake for some limitations of the language, which we understand and are working on overcoming. So we still need C code, basically C interfaces for dealing directly with device registers and other shared memory and a few other things. So there's limitations there, but it's on the right track at least. And we know that it should be suitable for implementing not general system code necessarily, but the sort of stuff we're building in the Lions OS. Performance, well, it performs less than less than C implementations, still better than Linux. So this is the CPU, this is the pure SDDF, this is the Pancake, the SDDF with the Pancake multiplexers, and this is Linux. If everything was written on Pancake, we probably wouldn't be faster than Linux. So there's definitely performance issues, but we understand where they're coming from. They're basically a result of Pancake being sort of inherited from this high-level CakeML language where a program expects to be the only thing in the world, and it doesn't have a notion of shared memory, it doesn't have a notion of being called as a function from outside, etc. We're working on that. And then quick update on other developments. One recent IFC was submitted by my former student Mitch on budget limit threshold. So this fixes a major hole in the MCS model. Remember, MCS has this notion of scheduling context where a server can run on the scheduling context of its clients, and the client gets charged for the time, and that makes the accounting proper and has a lot of nice advantages. The problem is there's no guarantee that the client's budget doesn't expire while in the server, and you need complex recovery logic, which is sort of the opposite of what we want, right? It forces complexity on your design, and we should never do that. What this RFC proposes budget thresholds where you can tag an endpoint with a threshold, and the client will only be able to call the server when it has at least that much budget left. And that makes budget expiry from a regular case to an actual error condition where the server is stuffed up. And so it becomes a normal error condition and simplifies the design dramatically. So please have a look at that one. There's so far no comments on it. There's also the RFC for the driver framework. Lucy gave an update. It's not yet ready to be pushed. There's still too much of the design to be resolved. So probably in a year, we might be at the point where we can really push that into the foundation. At the moment, it's still out there for discussion. And then there's the time protection work, which I'm just mentioning because it's on hold. We run out of money for that one. And provably secure general purpose OS, so this is the fully dynamic OS. We actually do have an idea of how the security works in such a system, but it's not progressing very quickly because we don't have external funding to us, so it's just driven by a few students. Okay, so in summary, My real takeaway from the past 9 months really is simplicity wins. It's simplicity wins in performance as well as in robustness and verifiability. And so that's the basis on which to really build a proper operating system. And that's the Lions OS. Pancake, I would call the jury still out. It's on the right track, it's promising. It's not guaranteed it will achieve what it's meant to be, but I hope it will. And that's it. Thank you.
Thank you. If we're willing to borrow a minute or two from the break, we can do a few questions.
I have to comment because you said there's a major hole in the MCS design.
I think I called it a weakness or something, or a
said hole.
deficiency.
But my comment is, are you requiring a budget on the server? Because
No, this is going to be optional.
yeah, because the server, then the complexity goes to the server now needs to know how long it's going to take.
Well, if you want to keep your server simple, you do it. But
Right, but I wouldn't call that simple. So I think that both options are valid and it's a good extension.
no, your server will become way simpler for sure if you do it right.
Sure, assuming it's simple to work out how much time it's going to take.
Well, that's the problem of having a real-time system. You really need to know what your worst-case execution times are, otherwise you can't do real-time. If you don't do real-time, then budget expiry is not a problem. You just wait till the budget gets refreshed.
Hi. In your example use cases, you mentioned cyberphysical systems, IoT stuff, embedded stuff. That's all sounds like fairly static use cases to me. In your definition of real world and complete, do you include systems that one might sit at and type on that would be a more dynamic workload? Do you aspire to cover that in Lions OS? And if so, what does the path to that look like?
Well, we're specifically limiting ourselves for now to the space of cyberphysical, IoT, etc. systems. Things that where a static architecture really works well. I make no claims going beyond that yet.
Thank you.
So that was sort of my question, was the relation, you mentioned the provably secure general purpose system at the end. I was just going to ask what the relationship was between that and the Lions OS, but I think you sort of half answered that.
So it's a completely different development. It will be able to reuse a lot of the stuff we do for Lions OS, but it's completely decoupled.
So I really like the idea of radical simplicity, but it's also a trade-off which moves some of the complexity from runtime to configuring the system and also the build system. So how do you ensure that it doesn't become an issue?
I don't see how it can become an issue, because you can replace your policies, right? We don't force you to have one policy. And I said you can even replace it at runtime, or you can build a policy module that is arbitrarily complex if that you really think you need that. I would like to see the use case, because I don't believe you need that, but it's a separate story, right? The point is you don't have to carry all this baggage along. You're welcome to take as much baggage on the flight as you like. I'm not stopping you, but I don't want to force anyone to use extra baggage.
All right.
All right, we're 5 minutes in the break, so I think it's time for us to go relax for a bit. So yeah, thank you so much, Gernot.